The Soviet Union built a 640-ton aircraft that could carry entire locomotives, a tank with 5 turrets requiring 12 crew members, and a missile-launching boat that flew just above water at 340 miles per hour. While the West focused on practical engineering, Soviet designers created machines so outrageous, they seemed pulled from science fiction. These weren't concept drawings or propaganda fantasies, they were real, operational vehicles that pushed the boundaries of physics and common sense. Welcome to the most insane chapter of military engineering history. The Antonov An-225 Mriya, the Sky Titan. A single aircraft engine failure would ground most planes, but the An-225 Mriya could lose 3 of its 6 engines and still fly safely. This Ukrainian-built monster wasn't just the world's largest aircraft, it was a flying impossibility that redefined what could take to the skies. Stretching 275 feet long with a wingspan wider than a football field, the Mriya weighed 640 tons when fully loaded. Its cargo hold could fit 50 cars or house 4 crew members comfortably in its engineering bay. The aircraft required 32 wheels just to distribute its massive weight on runways, with 20 of those wheels being steerable for ground maneuvering. Originally designed to piggyback the Soviet Buran space shuttle, the Mriya became a commercial cargo hauler after the space program ended. It routinely transported objects once thought impossible to move by air: 130-ton generators, wind turbine blades longer than most aircraft, and even diesel locomotives. The sight of this 6-engine giant attracted crowds wherever it landed, becoming a symbol of Ukrainian engineering pride. The aircraft's unique design featured twin vertical stabilizers and engines mounted above the wings to avoid ground debris when loading oversized cargo. Its maximum altitude of 36,000 feet meant it could fly intercontinental routes while carrying payloads that would require multiple cargo ships to transport by sea. Tragically, the only completed Mriya was destroyed during the 2022 Russian invasion of Ukraine, ending the operational life of aviation's most ambitious achievement. The T-35 heavy tank, the land battleship. Imagine a tank so massive it needed 11 crew members and got lost because its own turrets blocked the driver's vision. The T-35 wasn't just a tank, it was a mobile fortress that embodied Soviet excess in armored warfare. At 45 tons and nearly 32 feet long, the T-35 featured 5 turrets bristling with weapons: one 76mm main gun, 2 45mm cannons, and up to 7 machine guns. This firepower required a crew larger than most aircraft, with gunners, loaders, and commanders spread across separate fighting compartments that couldn't communicate effectively with each other. The tank's design philosophy assumed it would break through enemy lines while creating a sea of fire around itself. In reality, the T-35 proved mechanically unreliable and strategically useless. Its 500-horsepower engine could barely push the massive hull to 19 miles per hour on roads, and cross-country mobility was practically non-existent. Only 61 T-35s were ever built, making them more valuable as parade vehicles than combat weapons. During World War II, most T-35s were lost to mechanical breakdowns rather than enemy action. The few that saw combat were quickly destroyed or abandoned when their complex systems failed under battlefield conditions. The T-35 represented the interwar period's obsession with multi-turreted land battleships, a concept that looked impressive on paper but proved disastrously impractical in real warfare. It remains the only 5-turreted tank ever to reach mass production, a testament to Soviet willingness to build the impossible. The Lone-class Ekranoplan, the flying warship. Soviet engineers created a 240-foot missile-armed vehicle that wasn't quite a plane and wasn't quite a ship. It was something entirely new that skimmed across water at 340 miles per hour while carrying enough firepower to sink an entire naval fleet. The Lone-class Ekranoplan exploited ground effect physics, using the air cushion created between its massive wings and the water surface to achieve lift without actually flying. This allowed the 240-ton vehicle to cruise just 13 feet above the waves, too low for radar detection but too fast for naval defenses. Armed with 6 P-270 Mosket anti-ship missiles, the Lun could engage targets 75 miles away while remaining virtually invisible to enemy sensors. Its 8 turbojet engines provided enough thrust to accelerate this flying fortress to speeds that would make most naval vessels look stationary. The craft's unique design challenges included saltwater corrosion from constant spray, limited operational conditions requiring calm seas, and the need for specially trained pilots who understood both aviation and maritime operations. The International Maritime Organization classified ekranoplans as ships rather than aircraft, creating regulatory confusion that persists today. Only one Lune-class ekranoplan was completed before the Soviet Union's collapse ended the program. The surviving vehicle now sits as a museum piece on the Caspian seashore, a reminder of Soviet ambitions to revolutionize naval warfare through physics-defying engineering. The Buran Space Shuttle, the Soviet Space Phantom. While NASA's space shuttle required pilots for every mission, the Soviet Buran accomplished something American engineers thought impossible. It flew to orbit and landed completely unmanned, controlled entirely by computers in an era when most people had never seen a personal computer. The Buran program represented the Soviet Union's most expensive space project, involving over 1,000 companies across the country. Unlike the American shuttle, which carried its main engines into orbit, Buran rode atop the massive Energia rocket, making it a true passenger spacecraft rather than a rocket-powered aircraft. On November 15, 1988, Buran completed its only spaceflight, a flawless two-orbit mission lasting 208 minutes. The spacecraft launched automatically, maneuvered in orbit using onboard computers, and executed a perfect runway landing without any human intervention. This automated capability was decades ahead of its time, predating modern autonomous vehicle technology by 30 years. The shuttle's cargo bay could accommodate satellites up to 56 feet long, and its crew cabin was designed for 6 cosmonauts. Additional crew members could ride in the cargo area for specialized missions. The spacecraft's heat shield used different materials than NASA's shuttle, optimized for the harsh conditions of Soviet launch sites. Despite its technological success, Buran never flew again. The Soviet Union's collapse in 1991 ended funding for the program, and the only operational orbiter was destroyed in 2002 when its storage hangar collapsed. The program's cancellation marked the end of Soviet dreams of routine space transportation. The VDNKH robot, the Soviet android dream. In 1959, when most people thought robots existed only in science fiction, Soviet engineers unveiled a 1.8-meter humanoid robot that could execute 18 commands, respond to light and sound, and perform for amazed crowds at Moscow's VDNKH Exhibition Center. The VDNKH robot represented the Soviet Union's early experiment in humanoid robotics, designed to showcase technological superiority during the Cold War. Standing on a specially built stage in front of the electrification pavilion, the robot performed demonstrations every 2 hours, combining engineering achievement with theatrical showmanship. This early android could perform basic human movements, respond to voice commands, and navigate simple obstacles using primitive sensors. While crude by modern standards, the robot's capabilities were revolutionary for the 1950s, predating industrial robotics by decades, and demonstrating Soviet commitment to automation technology. The robot's design philosophy reflected Soviet optimism about human-machine collaboration, envisioning a future where robots would support workers in factories and daily life. Its public demonstrations captured imaginations and inspired a generation of Soviet engineers to pursue robotics research. The VDNKH robot's legacy extends beyond its mechanical capabilities to its cultural impact, representing a time when robotics was emerging as a field full of promise. It embodied the Soviet Union's drive to innovate through technology, blending practical demonstration with symbolic hope for technological progress that would define the space age. The MAZ-7907, the 24-wheeled nuclear nightmare. Soviet engineers built a truck so massive it needed 24 wheels, 2 tank engines, and electric motors at every wheel, just to move a 100-ton nuclear missile across rough terrain. And only 2 of these mechanical monsters were ever completed. The MAZ 7907 stretched 92 feet long and weighed 66 tons empty, designed specifically to transport the RT-23 Molodets intercontinental ballistic missile. This road-mobile nuclear launcher represented the ultimate expression of Cold War mobility, capable of carrying world-ending firepower to any location accessible by road. 2 1,250 horsepower gas turbine engines from T-80 tanks powered electric generators that fed individual motors at each of the 24 wheels. This turbine electric drive system allowed the massive vehicle to navigate rough terrain while maintaining the precision needed for missile deployment. 8 of the 12 axles were steerable, enabling surprisingly tight turns for such a massive vehicle. The truck's articulated frame and independent hydropneumatic suspension for each wheel helped it traverse difficult terrain without losing stability. Despite weighing over 200 tons when loaded, the MAZ 7907 could achieve speeds of 25 miles per hour on roads and maintain mobility across unpaved surfaces that would stop conventional vehicles. The end of the Cold War eliminated the need for road-mobile nuclear missiles, leaving the MAZ 7907 without a mission. One surviving chassis was later used to transport an 88-ton ship 250 kilometers across Belarus, proving the vehicle's incredible load-carrying capability, even in civilian applications. The Caspian Sea Monster, the original Ekranoplan. American spy satellites detected something so bizarre skimming across the Caspian Sea that CIA analysts couldn't determine if it was a plane, a ship, or something entirely new. They simply called it the Caspian Sea Monster, and it became one of the Cold War's most mysterious weapons. The KM, or Korabl Maket, was the world's first operational ground effect vehicle, a 348-foot experimental craft that flew just above the water surface using 8 massive turbojet engines. Weighing over 540 tons, it was simultaneously the heaviest aircraft and fastest ship ever built when it began testing back in 1966. This flying Leviathan exploited ground effect physics to achieve impossible performance, skimming across water at speeds up to 460 miles per hour while remaining invisible to radar. Its massive size, longer than a Boeing 747 with engines producing 127,000 pounds of thrust, made it detectable by satellites but honestly, incomprehensible to intelligence analysts. The KM's experimental nature meant constant testing and modification throughout its operational life. Soviet engineers used it to develop techniques for ground effect flight, leading to later military applications like the Lund-class Ekranoplan. Its unique capabilities included the ability to carry massive payloads at aircraft speeds while operating from any large body of water. The monster's career ended in 1980, when pilot error caused it to crash into the Caspian Sea during a test flight. No lives were lost, but the unique vehicle sank and remains on the sea floor, taking with it secrets of Soviet ground effect technology that took decades to fully understand. The Zveno flying aircraft carrier, the aerial mothership. Soviet engineers solved the problem of limited fighter aircraft range by creating something that sounds like science fiction. A massive bomber that carried smaller fighter planes on its wings and released them in mid-air for combat missions. The Zveno project transformed a TB-3 heavy bomber into a flying aircraft carrier, mounting up to 5 smaller aircraft on its wings and fuselage. I-16 fighters would attach to the bomber before takeoff, ride to the target area, then detach for independent combat operations before returning to land at conventional airfields. This aerial mothership concept addressed the fundamental limitation of 1930s fighter aircraft. Their short range made them useless for long-distance missions. By carrying fighters to the battle zone, the Zveno system extended their operational radius by hundreds of miles, effectively creating mobile air bases that could appear anywhere within the bomber's range. The system required extraordinary pilot skill and precise coordination. Fighter pilots had to attach their aircraft to the bomber's wing mounts, ride through potentially turbulent flight conditions, then detach cleanly without colliding with the carrier aircraft or other fighters. The complexity of these operations limited the system's practical applications. Despite successful testing and limited combat use during World War II, the Zveno concept was abandoned as aircraft technology advanced. Longer-range fighters and aerial refueling made the flying aircraft carrier unnecessary, but the project demonstrated Soviet willingness to pursue unconventional solutions to tactical problems. The 1K-17 Shotty laser tank, the Soviet death ray. While science fiction promised laser weapons in the distant future, Soviet engineers built a working laser tank in the 1970s that could blind pilots and destroy optical equipment using focused light beams generated by synthetic rubies weighing 66 pounds each. The 1K-17 Shotty mounted an array of 13 laser emitters on a tank chassis, each focusing powerful light through synthetically grown rubies to create coherent beams capable of damaging enemy equipment. Unlike modern military lasers designed to burn through targets, the Shotty was built to blind and disorient rather than destroy. The system's ruby-based laser technology represented cutting-edge Soviet research into directed energy weapons. Each ruby crystal required precise manufacturing and alignment to focus the laser beams effectively, making the entire system incredibly complex and expensive to maintain. Combat applications included disabling enemy optical systems, blinding pilots during low-level attacks, and potentially damaging sensitive electronic equipment. The laser array could fire in pulses to prevent overheating while maintaining effectiveness against multiple targets. The Shatya never saw combat deployment, remaining an experimental system throughout its development. The complexity of maintaining the laser array, combined with the emergence of more practical anti-aircraft systems, led to the program's cancellation. However, the technology developed for the Shatya influenced later Soviet research into directed energy weapons. The Bartini-Beriev VVA-14, the Soviet Millennium Falcon. 5 years before Star Wars introduced the Millennium Falcon, Soviet designers created an aircraft that looked like it came from a galaxy far, far away. A vertical takeoff amphibious plane designed to hunt American submarines anywhere in the world's oceans. The VVA-14's bizarre elliptical shape served multiple purposes. The entire fuselage acted as a lifting body, while inflatable pontoons allowed water operations and vertical takeoff capability. This unique design enabled the aircraft to operate from land, water, or even rough seas where conventional seaplanes would be destroyed. Designed by Italian engineer Roberto Bartini, working in the Soviet Union, the VVA-14 was intended to counter American Polaris submarine-launched ballistic missiles. The aircraft would patrol vast ocean areas, using its amphibious capabilities to land on water for extended surveillance missions or emergency operations. The prototype's test flights revealed both the promise and problems of its unconventional design. While the lifting body concept worked, the complex systems required for vertical takeoff and amphibious operations proved unreliable. The aircraft's unique appearance and advanced capabilities made it a showcase of Soviet aerospace ambition. Only one prototype was completed before the program ended in the mid-1970s. The VVA-14's influence on science fiction design is unmistakable, and its advanced concepts predated modern vertical takeoff aircraft by decades. The surviving prototype remains a testament to Soviet willingness to pursue revolutionary aircraft designs. These 10 mechanical monsters prove that Soviet engineers never met an impossible idea they wouldn't try to build. From flying tanks to nuclear-powered trucks, they created machines that pushed physics to its limits and common sense beyond recognition. While many failed spectacularly, others achieved the impossible and changed military technology forever. What's your favorite Soviet engineering nightmare? Share your thoughts below. Hit that like button if these crazy machines amazed you, and subscribe to Future Facts for more incredible stories of human ingenuity gone wild. Until next time, keep questioning everything. Deep beneath the Swiss-French border, CERN's Large Hadron Collider has achieved something that honestly sounds like science fiction, creating conditions so extreme they may have briefly formed microscopic black holes. Now these aren't the massive cosmic devourers we know from space, but quantum-scale phenomena that exist for mere fractions of a second before evaporating in bursts of exotic particles. What scientists discovered in the aftermath of these experiments has, well, profound implications for our understanding of extra dimensions, quantum gravity, and the fundamental structure of reality itself. The theoretical foundation. The real secret behind microscopic black hole creation lies in some pretty cutting-edge theories about the nature of space itself. In standard physics, creating a black hole would require concentrating energy equivalent to around 10 to the 19th GeV, way beyond what any human-made machine could ever achieve. But theories involving extra dimensions like the Arkani-Hamed-Dimopoulos-Dvali or ADD model suggest that gravity might actually leak into hidden spatial dimensions while other forces stay confined to our familiar three-dimensional space. This would explain why gravity seems so much weaker than electromagnetic or nuclear forces. It's not inherently weak, but rather it's diluted across extra dimensions we just can't perceive. If this is true, it dramatically lowers the energy threshold for black hole formation, potentially bringing it within reach of the LHC's 13 to 14 TeV collision energies. The mathematical framework for these ideas really started to take shape around 1998 to 2000, when physicists like Nima Arkani-Hamed, Savas Dimopoulos, and Gia Dvali proposed that our universe might have more than the 4 dimensions we experience. These extra dimensions would be compactified, curled up so tightly at every point in space that we can't detect them in everyday life, yet they fundamentally alter how physics works at the tiniest scales. CERN's experimental setup. The Large Hadron Collider represents, honestly, humanity's most ambitious attempt to recreate conditions from the earliest moments of the universe. Built in a 27-kilometer tunnel beneath the Swiss-French border, the LHC accelerates protons to 99.9999991% of light speed before smashing them together with unprecedented energy. The ATLAS and CMS detectors, which are just massive instruments containing millions of sensors, capture the spray of particles created in these violent collisions. When protons collide at such extreme energies, they create conditions similar to those existing just a fraction of a second after the Big Bang, when temperatures exceeded 1,000,000 billion degrees. The detectors track every particle emerging from these collisions, always on the lookout for signatures of new physics beyond the standard model. The CMS, or Compact Muon Solenoid experiment, has been specifically searching for microscopic black hole signatures ever since the LHC's early runs. These searches focus on identifying the distinctive particle showers that would result from black hole evaporation through Hawking radiation. The detectors have to distinguish between ordinary particle collisions and the unique signatures that would indicate space-time itself has temporarily collapsed into a microscopic black hole. The search for microscopic black holes. The CMS collaboration has, conducted extensive searches for microscopic black hole production throughout the LHC's operational history. During the 2010 run at 7 TeV center of mass energy, scientists analyzed proton-proton collision data, looking for the distinctive signatures that would indicate black hole formation and subsequent evaporation. According to theoretical predictions, if microscopic black holes formed, they would immediately evaporate through Hawking radiation, producing a characteristic spray of subatomic particles. These particles would create specific energy patterns detectable by the CMS detector's sophisticated sensors. The evaporation process would happen in about 10 to the -27th seconds, an almost incomprehensibly brief moment. The search parameters focused on black hole masses ranging from 3.5 to 4.5 TeV, based on various theoretical models involving extra dimensions. Scientists looked for events where particles emerged in patterns consistent with black hole decay, including high-energy jets and unusual particle multiplicities that just wouldn't occur in standard particle collisions. While no definitive evidence for microscopic black holes has been confirmed in peer-reviewed publications, the searches have provided valuable constraints on theoretical models and continue to refine our understanding of what might be possible at these extreme energy scales. Stephen Hawking's encouragement. In 2009, renowned physicist Stephen Hawking visited CERN's underground facilities and made a remarkable statement that really captured the scientific community's imagination. While touring the ATLAS detector with CERN Director General Rolf Heuer, Hawking expressed his hope that the LHC would successfully create black holes, saying with characteristic enthusiasm, "I hope you'll make black holes." This wasn't just scientific curiosity. Hawking understood that creating microscopic black holes would represent a fundamental breakthrough in physics. Such an achievement would provide the first experimental test of quantum gravity, the long-sought theory unifying Einstein's general relativity with quantum mechanics. It would also offer direct evidence for extra dimensions and validate decades of theoretical work. Hawking's encouragement came despite ongoing public concerns about LHC safety. A lawsuit had actually been filed in the United States expressing fears that the collider might create dangerous black holes or exotic matter that could destroy Earth. The lawsuit was eventually dismissed on grounds that speculative fear of future harm does not constitute an injury in fact sufficient to confer standing. Hawking's support helped legitimize the scientific importance of these experiments, emphasizing that any microscopic black holes created would evaporate instantly through the radiation process he had theorized decades earlier. The Hawking radiation process. The theoretical framework for microscopic black hole evaporation relies on Stephen Hawking's groundbreaking work from the 1970s, which showed that black holes aren't completely black, but emit radiation through quantum effects at their event horizons. This process, known as Hawking radiation, happens because quantum mechanics allows particle-antiparticle pairs to spontaneously appear near the black hole's boundary. In this process, one particle from each pair falls into the black hole while the other escapes, carrying away energy and causing the black hole to gradually lose mass. For microscopic black holes, this evaporation happens almost instantaneously. The smaller the black hole, the faster it evaporates. A black hole with the mass of a proton would disappear in about 10 to the minus 27th seconds. The evaporation produces a distinctive signature, a burst of particles with specific energy distributions and correlations. These particles would include photons, electrons, muons, and potentially exotic particles not found in the standard model. The exact composition depends on the black hole's mass and the number of extra dimensions through which gravity can propagate. This rapid evaporation is crucial for safety. Any microscopic black holes created at the LHC would disappear before they could interact significantly with surrounding matter, making them scientifically fascinating but, practically harmless. Recent experimental developments. In 2024, CERN's High RadMat facility achieved a significant breakthrough by creating high-density electron-positron plasma beams that mimic the jets of matter and antimatter streaming from astrophysical black holes. The Fireball collaboration, led by researchers including Gianluca Sari, successfully produced plasma containing around 10 trillion electron-positron pairs, the highest density ever achieved in laboratory conditions. This experiment doesn't create actual black holes, but it recreates the extreme plasma conditions found in black hole jets, providing insights into how these cosmic phenomena behave. The research helps validate theoretical models of black hole physics using real experimental data rather than just computer simulations. Meanwhile, the search for actual microscopic black holes continues with increasingly sophisticated analysis techniques. Machine learning algorithms now scan collision data for subtle patterns that might indicate black hole formation and evaporation. These AI systems can detect correlations in particle tracks that human researchers might easily miss, potentially revealing evidence of quantum gravitational effects. The CMS and ATLAS collaborations continue refining their search strategies, looking for soft, unclustered energy patterns. Subtle energy signals that don't form clear particle groups, but might indicate interactions with hidden dimensions or exotic physics beyond the standard model. Implications for extra dimensions. So, the search for microscopic black holes represents more than just an attempt to create exotic objects, it's actually a direct probe of spacetime's fundamental structure. If these black holes can be created at LHC energies, it would provide the first experimental evidence for extra dimensions beyond the three spatial dimensions we experience every day. The existence of extra dimensions would totally revolutionize our understanding of physics, and could explain why gravity appears so much weaker than the other fundamental forces. It would also suggest that our familiar three-dimensional space is just a brain embedded in a higher dimensional reality, with gravity able to propagate through the full multidimensional space, while other forces remain confined to our brain. Different theoretical models predict different numbers of extra dimensions, from one additional dimension in some scenarios, to 6 or even more in others. The energy threshold for black hole creation, and the characteristics of their evaporation, would reveal crucial information about these hidden aspects of reality. And, such discoveries would also have profound implications for cosmology, potentially explaining dark matter and dark energy as manifestations of physics operating in extra dimensions. So, the microscopic black holes created at CERN might provide the first laboratory window into these cosmic mysteries. Safety considerations and natural experiments. So, before launching any high-energy experiments, CERN scientists, really took their time with extensive safety assessments, especially when it came to concerns about microscopic black hole creation. The main argument for safety actually comes straight from nature. Cosmic rays are constantly bombarding Earth's atmosphere with energies that, honestly, far exceed anything the LHC could ever produce. Ultra-high-energy cosmic rays can carry energies up to 10 to the 20th power electron volts, which is, wow, about 10 million times higher than the LHC's maximum energy. These particles have been creating natural collisions with atmospheric nuclei continuously, and Earth has experienced roughly 1 million of these impacts per square kilometer every year for its entire 4.5 billion year history. If microscopic black holes posed any danger at the energies CERN explores, nature would have already run these experiments countless times over. The simple fact that Earth is still here shows that any black holes created at these energy scales either evaporate harmlessly through Hawking radiation, or are just way too small to interact significantly with ordinary matter. And even if Hawking's theory turned out to be wrong and microscopic black holes didn't evaporate, they'd still pose no threat because of their incredibly weak interaction with normal matter. Such objects would just pass through Earth almost without any effect, kind of like the trillions of neutrinos that pass through our bodies every second without us ever noticing. Future prospects and upgraded searches. Looking ahead, as the LHC keeps running with upgraded detectors and higher luminosity, the search for microscopic black holes is, well, becoming more and more sophisticated. The high luminosity LHC, which is expected to start up in the late 2020s, will actually provide 10 times more collision data, and that will dramatically improve our sensitivity to rare phenomena. Future experiments are going to use advanced artificial intelligence to analyze all that collision data, searching for subtle patterns that could hint at black hole formation. These AI systems can process vast amounts of data at the same time, spotting correlations and anomalies that would honestly be impossible for human researchers to catch manually. Then there's the proposed Future Circular Collider, a 100-kilometer ring that would operate at much higher energies than the current LHC, which could, in theory, give us a definite answer about microscopic black hole production. Running at energies up to 100 tera-electron volts, this facility would probe energy scales where extra-dimensional effects should, become really clear. Beyond just searching for black holes, these experiments keep pushing the boundaries of fundamental physics, seeking evidence of things like supersymmetry, dark matter particles, and other phenomena that could totally revolutionize our understanding of the universe. Every single collision gives us new data about the deepest levels of reality. The quest for quantum gravity. The quest for quantum gravity is really at the heart of this search for microscopic black holes. It's humanity's most direct attempt to probe the elusive theory that would finally unify Einstein's general relativity with quantum mechanics. Creating and studying these tiny objects would, for the first time, give us experimental data on how gravity behaves at quantum scales. These experiments could help resolve some of the most fundamental paradoxes in physics, like the black hole information paradox that's puzzled scientists for decades. If we can create microscopic black holes and study their evaporation in detail, it might finally tell us whether information falling into black holes is truly lost, or if it's somehow preserved in the radiation they emit, and the implications go way beyond just academic physics. Understanding quantum gravity could potentially unlock new technologies based on manipulating space-time, maybe even leading to advances in energy generation, transportation, or our understanding of consciousness itself. The microscopic black holes created at CERN might actually be the first steps toward a truly unified theory of everything. As scientists keep pushing the boundaries of what's possible, each experiment brings us a little closer to answering the deepest questions about the nature of reality. And whether or not microscopic black holes have actually been created, the search itself has already advanced our understanding of the universe's fundamental structure. So in the end, the quest to create microscopic black holes at CERN is really about more than just scientific curiosity. It's humanity's attempt to probe the deepest levels of reality itself. Whether these quantum-scale phenomena have been successfully created or, still remain tantalizingly out of reach. The search has already revolutionized our understanding of space-time, extra dimensions, and the fundamental forces that govern our universe. As technology keeps advancing and new experiments push ever deeper into the quantum realm, we're edging closer to answering the ultimate questions about existence itself. The universe's deepest secrets may finally be within our grasp. For over 5 decades, humanity believed NASA led the race to Mars. But, recently, declassified KGB documents reveal a shocking truth. Between 1960 and 1973, the Soviet Union actually launched 19 secret missions to Mars. Most of them ending in catastrophic failures, all buried under layers of Cold War secrecy. While Americans celebrated their public victories, USSR engineers were fighting a shadow war in space, desperately trying to beat America to the Red Planet. Hidden behind those generic Cosmos designations, these missions were basically erased from history. Today, we uncover the shocking truth about Soviet Mars exploration that nearly conquered another world. The secret war begins. October 1960 marked humanity's very first attempt at interplanetary exploration, and it exploded in, well, spectacular fashion. Soviet engineers at Baikonur Cosmodrome watched helplessly as their modified R-7 ICBM carrying Mars 1960A veered wildly off course just seconds after liftoff. The self-destruct command was sent immediately, obliterating the spacecraft and any evidence of the mission. 4 days later they tried again with Mars 1960B. This time the rocket reached Earth orbit, but the upper stage failed to ignite, leaving the probe stranded. Within hours, it re-entered the atmosphere and burned up completely. Both missions were quickly reclassified as generic Cosmos satellites to hide their true purpose from the world. The American press dubbed these mysterious launches Marsnik, a combination of Mars and Sputnik, but Soviet officials never acknowledged their existence. This began a pattern of secrecy that would define their Mars program for over a decade, with failures systematically erased from public records while engineers worked frantically behind closed doors. The first success. November 1962 brought a breakthrough that, honestly, changed everything. Mars 1 became the first Soviet spacecraft to successfully escape Earth's gravitational pull and head toward the Red Planet. Launched on November 1st, this 894-kilogram probe represented a massive leap forward in Soviet space technology. Chief designer Sergei Korolev had personally overseen the mission, equipping Mars 1 with a magnetometer, radiation detectors, cosmic dust sensors, and instruments designed to detect water vapor in the Martian atmosphere. For 124 days, the probe coasted through deep space, transmitting 61 successful communications back to Earth. Soviet mission controllers watched with growing excitement as their spacecraft traveled 193 million kilometers toward Mars. Then, on March 21, 1963, with Mars finally coming into view, all contact was suddenly lost. The most likely cause was a gas leak in the attitude control system, causing the spacecraft's antenna to drift off alignment. Mars 1 had proven interplanetary flight was possible, establishing the Soviet Union as a legitimate competitor in the race to explore other worlds. But it would remain forever silent in the void. The plasma engine experiment. Late 1964 witnessed the launch of Zond 2, carrying revolutionary technology that, honestly, wouldn't become mainstream for decades. Soviet engineers had equipped this 950-kilogram spacecraft with 6 experimental plasma thrusters, cutting-edge propulsion systems using electrically charged gas instead of traditional chemical rockets. Mission director Georgy Babakin believed these ion drives could provide precise course corrections during the long journey to Mars. The probe also carried an infrared spectrometer specifically designed to detect potential vegetation on the Martian surface, a bold scientific gamble that really reflected Soviet optimism about finding life. For nearly 6 months, Zond 2 flew steadily toward its target, with the plasma engines performing flawlessly during initial tests. Ground controllers conducted several successful engine burns, proving the revolutionary propulsion system worked in the harsh environment of deep space. But as the spacecraft approached Mars in August 1965, telemetry signals began weakening dramatically. Ground control lost all contact just as Zond 2 flew past Mars at a distance of approximately 1,500 kilometers. The probe had missed its flyby target by mere hundreds of miles, another agonizing near success that demonstrated Soviet engineering capabilities while highlighting the brutal challenges of interplanetary navigation. The mystery gap. Between 1965 and 1969, something extraordinary happened. The Soviet Mars program went completely dark. There were no public launches, no mission announcements, no press coverage whatsoever. Western intelligence agencies, honestly, they noticed this suspicious silence and began questioning what the USSR was planning behind closed doors. Internal documents later revealed that Soviet engineers were working frantically on their most ambitious project yet, simultaneous orbiter-lander missions that, well, would make American efforts look primitive by comparison. Chief designer Sergei Korolev's death in January 1966 had thrown the program into chaos, but his successor, Vasily Mishin, pushed forward with even grander plans. Teams worked around the clock developing heavy-lift proton rockets, advanced communication systems, and sophisticated landing capsules capable of soft touchdown on the Martian surface. The 4-year silence wasn't abandonment. It was preparation for an assault on Mars unlike anything attempted before. Secret facilities across the Soviet Union manufactured hundreds of specialized components, from heat shields designed to withstand Martian atmospheric entry to miniaturized scientific instruments capable of surviving the journey. By 1969, they had built the largest, most advanced interplanetary spacecraft in human history, ready to claim the Red Planet for the Soviet Union. The Great Explosions. March 27, 1969 brought one of the most catastrophic failures in Soviet space history. Mars 1969A, a massive bus-sized spacecraft loaded with cutting-edge instruments, sat atop a 190-foot Proton-K rocket at Baikonur. The mission was designed to place a heavy orbiter around Mars while simultaneously landing a surface probe, an unprecedented dual achievement that would, honestly, humiliate NASA's smaller efforts. At T0, the 4 first-stage engines ignited with 2.4 million pounds of thrust, lifting the enormous payload skyward. Then, 51 seconds after liftoff, disaster struck. The rocket exploded in a fireball so massive it shattered windows in villages 40 kilometers away. Flaming debris rained across the Kazakh steppes for miles, with wreckage scattered across an area larger than Manhattan. 5 days later, Soviet engineers tried again with Mars 1969B. This time, the first stage worked perfectly, but during stage separation, the upper stage failed catastrophically. The multi-million-dollar spacecraft tumbled back into Earth's atmosphere and disintegrated over the Pacific Ocean. 2 state-of-the-art Mars missions had been obliterated within a single week, representing months of preparation and millions of rubles lost in spectacular fashion. First contact with Mars. November 1971 marked the moment Soviet technology finally touched another world. Mars 2 and Mars 3 represented the USSR's most sophisticated interplanetary missions ever attempted, each carrying both an orbiter and a landing capsule. Mars 2 arrived first on November 27, with its lander screaming into the thin Martian atmosphere at over 20,000 kilometers per hour. But catastrophe struck when the parachute system failed to deploy properly. The descent module crashed, becoming the first human-made object to impact Mars, though not exactly as planned. 4 days later, Mars 3 approached for its landing attempt during one of the worst global dust storms ever recorded on Mars. The massive storm covered nearly the entire planet, creating atmospheric conditions that would challenge even modern spacecraft. Miraculously, everything worked perfectly. The parachutes deployed, the retro rockets fired, and the lander touched down softly in the Martian soil. For 90 seconds, Soviet mission control received clear signals from the red planet's surface, including the first attempted television transmission from Mars. Then, abruptly, the transmission died. Mars 3 had achieved the first successful soft landing on Mars, but survived less than 2 minutes in the hostile environment. The Lost Rover. Hidden inside Mars 3's landing capsule was a revolutionary piece of technology that, honestly, never got its chance to make history. Prop M, Pribor Otsenki Prokotomosti Mars, was the world's first interplanetary rover, a 4.5-kilogram robotic explorer designed to photograph the Martian surface and analyze soil composition. Built by Soviet engineers at Lavochkin, this lunchbox-sized robot moved on metal skis rather than wheels, connected to its mothership by a 15-meter tether that would transmit power and data. Prop M carried a dynamic penetrometer to test soil density and twin cameras for stereophotography. The rover was programmed to deploy automatically once Mars 3 confirmed a successful landing, waddling away from the lander like a mechanical insect exploring alien terrain. Its mission plan called for a systematic survey of the landing site, taking photographs and measurements that would guide future Soviet expeditions. But when the lander's systems failed after 90 seconds, Prop M never received its activation command. The tiny robot's computers never awakened, its cameras never opened, and its skis never touched Martian soil. For 50 years, this tiny Soviet robot has sat motionless inside Mars 3, buried somewhere in the Martian dust, humanity's first rover, forever waiting for a signal that will never come. The cover-up campaign. You know, the Soviet Union really perfected the art of making space failures disappear completely. Mission planners developed an elaborate system where any Mars probe that failed to leave Earth orbit would be immediately reclassified as a Cosmos satellite, a generic designation used for military payloads. This clever move allowed Soviet officials to claim they were simply testing Earth-orbiting technology, rather than attempting interplanetary exploration. It wasn't until decades later that Western analysts discovered the true nature of these missions through declassified documents and defector testimonies. For instance, Cosmos 21 was actually Mars 2 MV4A, a Mars flyby probe that never left orbit. Cosmos 419 was really Mars 8, a sophisticated orbiter-lander combination destroyed during launch. At least 6 additional Mars missions were hidden behind Cosmos designations, their true purposes buried in classified archives. Soviet engineers worked under tremendous pressure, knowing that failure meant not just technical setbacks but political humiliation that could end careers and send families to gulags. Success would be trumpeted worldwide as proof of communist superiority, but failure would be erased from history as if the missions never existed at all. This systematic deception created a false narrative that Soviet space exploration was more successful than reality. The final attempts. By 1973, the Soviet Mars program was bleeding money and credibility, but engineers pushed forward with 4 final missions that would either secure their place in history or end their Martian dreams forever. Mars 4, Mars 5, Mars 6, and Mars 7 represented the USSR's last coordinated assault on the Red Planet. Mars 4 was designed as an orbiter but suffered a computer malfunction and flew past Mars without entering orbit, becoming an accidental interplanetary probe. Mars 5 successfully orbited Mars and transmitted 60 images before radio failure ended the mission after just 9 days. Mars 6 achieved partial success, transmitting atmospheric data during descent before going silent just seconds before landing, tantalizingly close to becoming the second successful Mars lander. Mars 7 missed the planet entirely due to a mid-course correction failure, sailing helplessly past its target and into permanent solar orbit. The atmospheric data from Mars 6 proved invaluable, providing the first direct measurements of Martian air pressure and temperature during descent. After this series of near misses and partial successes, the Soviet Union quietly abandoned their Mars program. American Viking missions in 1976 would finally achieve what the Soviets had been desperately trying to accomplish for 16 years. The legacy of secrets. Today, declassified documents reveal that the Soviet Mars program was far more extensive and ambitious than the world ever knew. 19 separate missions were launched between 1960 and 1973, with only a handful achieving even partial success. Chief designer Sergei Korolev had envisioned Soviet cities on Mars by the 1980s, complete with mining operations and permanent colonies. Secret facilities across the USSR manufactured hundreds of spacecraft components, advanced life support systems, and even prototype spacesuits for Martian explorers. Internal reports from the 1960s show that Soviet leaders allocated massive resources to Mars exploration, viewing it as the ultimate propaganda victory over American capitalism. The program consumed enormous amounts of the Soviet space budget, with some estimates suggesting Mars missions received more funding than the lunar program during peak years. But technical limitations, political pressure, and budget constraints doomed most missions before they could prove their worth. The real tragedy wasn't just the engineering failures, it was the systematic erasure of these bold attempts from history. Thousands of Soviet scientists and engineers dedicated their careers to reaching Mars, only to have their efforts classified and forgotten for half a century. The Soviet Mars program remains one of history's greatest space secrets. 19 missions launched in complete secrecy, with most failures buried under Cold War classification. While NASA celebrated public victories, Soviet engineers were quietly achieving the first Mars impact, first soft landing, and first orbital insertion around the Red Planet. Their revolutionary technologies were decades ahead of their time. Though political secrecy erased their achievements from textbooks, these forgotten pioneers paved the way for every Mars mission that followed. Which Soviet Mars secret shocked you most? Drop your thoughts below. If you loved these hidden space mysteries, hit that like button, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible declassified discoveries.